Okay, so let's talk a little bit about the difference between k-means clustering and k-medoid clustering, which are quite similar but different in very important but little things. So, when we are doing k-means in the main idea, it's a type of an unsupervised learning in which we are dividing by seeding some points in the space. We are dividing the space to clusters, and this clustering is updating at each time until it converges and then it stops. Now there is a difference between the process we are doing in k-means and the k-medoids, which is quite similar but a little different. What's the difference? The difference is that k-means in each cluster we are calculating the centroid of the cluster, the main point of the cluster, which is called the centroid, is a mean of the points. Namely, we are taking all the points, summing and dividing by the number of points. Namely, taking the means if it's in coordinates, so taking the coordinate of each axis and taking the mean, and this is the point in space, which is the new centroid of the cluster. I'll talk a little bit about how we start the k-means a little bit later. Now, in the k-medoids, after we have clustering, we are taking the cluster itself, and we check which point of the cluster. Remember, in k-means, we just needed a point in the space. Now we need an instance of the cluster, namely a very specific point of the cluster, not just any point in the space as in the k-means, but in the k-medoid we need to find a specific point in the cluster points, and that's the main difference. We are looking for the medoid, which should be one of the points of the cluster. In k-means, it could be any point in the space. It's just the mean of the cluster. In k-medoids, we need a specific point of one of the points of the cluster, namely, medoid is a point of the cluster, is the point of the group. In the k-means, it's just a point in space, which is the mean of the points of the cluster. Now in the k-medoids, I'm looking for the point in the cluster which has the minimum total distance from all other points in the same cluster. This point in the cluster, which has the minimum sum of distance from all the other points in the cluster, this is the new medoid in the cluster. Now, how we do this clustering? In the k-means, we start by seeding the points. We can choose any seeding. In this example, there are two seeds, but we can take more. K is for the number of cluster. If I take K for 2, I will have 2 cluster. But if I took 10 seeds, namely 10 points, I will have 10 clusters. So the K stands for the number of seeds I put in the space, which will correlate with the number of cluster I will get. Here, they chose 2. So I can choose the 2 points in the start arbitrarily, randomly, or one of the points, or 2 points in the space, or 2 points in the one of the points. I take some points. Then I check for each point in the space which centroid, which seed is the closest to this point. The seed which is closest to this point, the seed, let's start with this, the seeds correlate with the cluster. Each seed is the cluster. If this point is closer to this point, so it means that it's part of the cluster of this point. If there is a point which is closer to this point than to this point, it means that this point is part of this cluster, of the cluster of this point. So I do it for each point. I check from which centroid it is closest to, and I devote this point to the cluster. So I do it for each point. This is how I define a cluster. Then in the cluster, I calculate the mean. The mean can be anywhere here. The same I do for this cluster. The mean can be anywhere here. Then I assign again each point to which new cluster, to which new centroid it is closest to. it can change. I do it until it converges, namely the means, the cluster are not changing and the means are not changing, and then I stop. In the k-medoids, I choose the two. I chose here two seeds. He chose from stack two seeds, but I could again take any arbitrary number of medoids to start with. I could take 10, for example. So it chose two. So we choose 2 points from the space, which is part of the points in the space, the points of the, let's say, I don't know, the data, not just any point in the space. And I chose 2 points. And what I do now, the assignment will be the same. I check for each point to which medoid, let's call it now, it is closest to. I assign this point to the medoid. This, I do it for each point. This creates in here two clusters. If I add more medoids, it will be more clusters. The number of medoids equal the number of cluster I will have. Here I have two medoids. So I will assign each point to the medoid which is closest to. This is how I created the clusters. Now when I have the clusters, I check which point in the cluster have the minimum sum of distances from all the points in the cluster. This point will be the new medoid of the cluster. The same I do for this cluster. Then again, I go from one point to the other and check from which medoid it is, for each medoid it is closest to. I assign it for this cluster. And again, I check which is the new medoid, which is the point in the cluster, which is the minimum sum of distances for from all the other points in the cluster. And I have the new medoids. Again, I do it again and again and again. Assign, update, assign, update, assign, update, until it converges, namely there is no change in the cluster and no change in the medoids. The advantage of medoids is it is a little bit less sensitive to outliers. Let's say I have an outlier which is here. If I take this cluster and I have an outlier which is here, the outlier will push the centroid, the mean of the cluster, to its side. So the mean might be here, which is not really the case. The mean should be here, even if there is an outlier. Most of the points are here, but because mean is sensitive to outliers, the mean could be somewhere here. In the medoid case, this is less sensitive to outlier. Why? Because if I have an outlier here, it will not change the medoid too much, because I will check which point is closest as the sum of distances to all other points. And of course, it won't be an outlier. It will be some point in here. Namely, it is less sensitive than the k-means to outliers. So this is the k-medoids. This is the k-means, which uses the centroids, the means, the centroids, also called the centroids. And you could, and in the means I check for the mean, and in the medoid I check the medoid will be the point from the data, and here it will be a point in space which is the mean, and in the medoid will be the point with minimum distance from the other point. In the mean it will just be the mean of the cluster. And if you look at it as an algorithm, the assignment in k-means will be the same as in k-medoids, assigning each data point to the nearest centroid, forming k clusters. And the update in k-means will be based on the mean. Calculate the new centroid as the mean of all data points in each cluster. In the medoid case, the assignment of each point will be the same, assigning each data point to the nearest medoid, forming k clusters. But the update rule will be different. For each cluster, we will choose the medoid. Select a new medoid such that the total distance between the medoid and all other points in the cluster is minimized. Okay? So k-means based on the means and centroid, and k-medoids based on the minimum distance, the medoid. And it does it until it converges. Thank you. If there are any corrections, please correct me. This was basically and mainly about the difference between k-means clustering and k-medoid clustering. Thank you very much, and that's is it.